Okay, let's start, Grigorii.
So, hello everyone. Today I'm going to talk about the Laplacian spectra of graphs, and I'm going to tell you the things that are written in the articles of the title, and the name of its author are here. But in this article, many things are not proved, are not proven, but there are plenty of references. So if you are interested in some details on any part of my speech, you can go here and find the references that you need. Okay, so we're going to consider graphs, and by default, all graphs that we consider are unoriented. And also, sometimes we will consider weight graphs.
You mean weighted or?
No, yes, I mean weighted.
Weighted.
And when I talk about a weighted graph, I mean the following thing. This is the graph when we and go to any pair of its vertices, we assign a weight, and the weight is symmetric. Also, the weight is non-zero if and only if two vertices are connected.
So the edges are weighted with some non-zero weights, yeah?
Yes, and we also assume that all weights are non-negative.
And so AUV, are they real numbers or integer numbers or?
U and V are
AUV, the weights.
The weights, they are real non-negative numbers.
Real positive, non-negative. Okay.
So many of the facts that I'm going to talk about will they are also true for the weighted graphs, but by default I would mean usual graphs, and also by default I will assume that graphs may have loops and multiple edges.
Loops and multiple edges allowed. Yeah. Okay.
Okay. The first notion that I want to introduce is the following. So, adjacency matrix. I suppose many of you heard about this notion, but
I believe there is A after J. Adjacency.
Yes. It won't be the main notion of this talk, but it is also useful to write it down. So if we have two vertices, I can consider a number AUV. It is a weight if we consider a weighted graph. Or if it's not a weighted graph, it is just the number of edges between U and V.
So in the last case, it is just a natural number, an integer.
And so I can consider adjacency matrix, which is just which consists of these AUV. So these row set numbers are labeled by vertices, and we just put in this matrix these numbers. A slightly different notion is
it's
Laplacian
useful to draw some simple example and give.
Okay, so let me draw it here. So let G be the following graph.
Probably let it make simpler, but add a loop, for example.
Okay. So then, what we have between vertices A1 and 2, we have 1 edge. So here I put 1, and here I also put 1. Then between 1 and 3, 1 edge. Between 2 and 3, we have 2 edges. And we have no edges between 1 and 1 and 3 and 3. So here I put 0, but we have one loop from 2 to 2. So here I put 1.
Mm-hmm. Great. And if there are weights, then there are no multiple edges, yeah?
Yes.
No multiple edges, provided the graph is weighted. То есть, если мы допускаем кратные ребра и кратные петли, если граф не взвешенный, тогда это отражается на матрице смежности, а если граф взвешенный, то кратные ребра уже не нужны, мы просто суммируем. Если были бы кратные ребра, мы бы просуммировали их веса и заменили одним ребром с общим весом. Окей.
Okay, then I'm going to introduce the main notion of the talk. It is Laplacian Matrix, the following. So I consider the adjacency matrix, and I consider the matrix D of G, which is just a diagonal matrix, which is also labeled by the vertices of the graph, and it has on the diagonal it has degrees of the vertices. So here dv is the degree of the vertex V. So it is the number of edges.
You may illustrate on this same graph. It will
So
be
we just consider a diagonal matrix, and on the diagonal we put degrees. So here we have two edges from 1, and we put here degree 2. The degree of vertex 3 is 3.
I would say
Oh,
5. Of 3, yeah, yes, you're right.
3 is 3, and of 2 it is 4.
5, I would say. The degree of vertex 2 should be 5, because there are 5 half edges leaving this vertex.
I suppose not, since the degree of the vertex, maybe there are different definitions, but the degree is just the sum of the values in the corresponding column or row. So just
it could be like that, but then probably you must have 2.
We should factor 1/2 because the loop has two morphisms.
Nope, that's a different theory. Okay, so at the moment we do not know how to deal with loops. We must be accurate here.
But I can say that this will not affect all the further, since the Laplacian matrix does not depend on the loop. That does not depend on this.
Okay.
Okay, let be here. Maybe 5 or 4.
Okay,
But
we'll see.
It doesn't affect Laplacians. Okay, so then
This is DOG.
DOG, and also we have Laplacian matrix, which is the difference of these two matrices. We should it is denoted by Q of G, and it is equal to D of G minus A of G.
So if you have 2 there in the middle, there, then the difference will be, then we must have 5. Okay. Negative 2.
No,
Difference in this
yes.
direction. 2 here, 1, 1. Yeah.
So here we have 3, here we have also 3. Here we have negative 1s. Here we have negative 2.
Great. So, and the Laplacian matrix must be degenerate. Yeah, it is always degenerate.
Yes, it has a eigenvalue. It has eigenvalue 0 since
The sum of, say, all rows is 0.
Yes.
Значит, если мы просуммируем все, скажем, столбцы или все строки, то мы получим 0. Это означает, что наша матрица вырождена. Это означает, что у нее есть собственное число 0. А это все равно. Мы можем здесь писать двойку, тогда здесь мы должны писать 5. Если мы здесь пишем единицу, то здесь мы пишем 4. Вот. А на разность двух матриц это не влияет. So the difference, it depends on how we define the adjacency matrix. Then the corresponding diagonal matrix will it will affect the diagonal matrix, but the difference will be the same.
Okay, so we are going to consider Laplacian spectrum, which is which consists of eigenvalues of Laplacian matrix, and I will denote it as following.
So if we erase, if we forget about this loop, then the Laplacian matrix will be exactly the same. So we, when studying Laplacians, we can not think about loops.
Вне диагонали меняем знак, а на диагонали добавляем, чтобы сумма в каждой строке была равна 0.
Exactly. So another definition is that we take the adjacency matrix, we make all the non-diagonal elements negative. We change the sign of all non-diagonal matrices, non-diagonal elements, and add diagonal elements so as to make the sum of elements in each column and each row equal to 0.
Yes. Well, the author of the article is sure that Laplacian matrix is more interesting and more deep than the adjacency matrix, and it is, maybe it's not surprising, because many results on graph invariants are can be formulated in terms of eigenvalues of the Laplacian matrix, and some of these results we will consider further. And I think that many of these results are indeed surprising.
I would say that
the blackboard on YouTube. Okay, I've posted links in chat.
Have you turned on А вы включили звук там? Вас услышали?
А там выключен?
Да.
Он включен, он включен.
Включен?
Да.
Хорошо.
Something's wrong?
No, it's okay. It's okay. But what I'm going to say is that since one of the matrices is reconstructed from the other one easily, I can't say that it's difficult to say whether the Laplacian is more important than the adjacency matrix. The Laplacian matrix can be reconstructed from the adjacency one.
Yes. No, but eigenvalues of can be some.
Yeah, eigenvalues
Can
are
be
different.
reconstructed such easily. No, okay, so it's
And lambda 1 is 0, yeah?
yes. So we have eigenvalues of the Laplacian. We numerate it in the increasing order, and yes, we have lambda 1 equal to 0. And I will also use such a notion. So I will write lambda k of G, meaning the kth eigenvalue of the Laplacian matrix of the graph G. Okay. Yes, here n is surely the number of vertices of the graph. Okay, then I'm going to formulate some basic properties of this of the Laplacian matrix. Firstly, it's almost obvious that all eigenvalues are real and non-negative. So and it allows us to write like this. Now, why it is so? Because our matrix is real and symmetric, and that's why all its eigenvalues are real. Well, now it's not so obvious why all eigenvalues are non-negative. So we write here lambda 1 equals 0, and it's true, and we know that one of the eigenvalues is 0, but we should prove that there are no negative eigenvalues. And I'm going to prove it in a moment. So just B says that the Laplacian matrix is positive semi-definite. And by the way, this implies that all eigenvalues are non-negative. And C, what about the multiplicity of the eigenvalue 0? It turns out that this multiplicity depends on the number of connected components in our graph, and namely multiplicity of 0 it is just equal to the indeed it is just equal to the number of connected components.
What we easily see is that the multiplicity of 0 eigenvalue is at least the number of connected components. So, because each connected component adds at least 1 0. Yeah?
Yes, if you have several connected components, then our matrix is just block matrix, which consists of blocks corresponding to components. Okay, let us prove this fact. Well, I have already said that all eigenvalues are real, and then I'm going to prove B, that our matrix is positive semi-definite. And in order to prove this, I should introduce some other notion. It is the following. So for any edge in our graph, I'm going to orient each edge in our graph. Namely, for each edge, I'm going to choose one of its of its ends and declare it the source, and I'm going to choose another and declare it the target. So for each edge, choose source and target. And when I do it for any edge, I obtain an orientation of our graph. And then we have a graph with orientation, then I can define oriented incidence matrix I will denote it by C. It will be labeled by, so it will have its rows will correspond to the vertices of our graph.
Значит, в матрице инцидентности, в отличие от матрицы смежности, у нее строчки нумеруются вершинами, а столбцы нумеруются ребрами. И в каждом столбце мы ставим единички, или там единички минус единички, в те клетки, которые являются концами соответствующего ребра. Is it true?
Yes. So we define it like this.
Это уже не квадратная матрица, она прямоугольная.
And an edge. Then we put 1 if this vertex is a target for this edge. And we put -1 if it is the source of E. And if they are not incident, this vertex and this edge, then we put 0.
То есть в каждом столбце две единички, одна с плюсом, другая с минусом. Вот. Остальные элементы столбца нули.
We have very simple equality which connects matrix C and the Laplacian matrix, and namely for each orientation of our graph we have the following. The Laplacian matrix equals to C multiplied by C transponent. So this,
Значит, матрица C, умноженная на C транспонированная, это уже будет матрица, у которой столько же строчек, сколько и столбцов. Это будет квадратная матрица размера n на n, где n число вершин, да, именно в этом порядке надо умножать.
Yes.
В этом. Вот. И это будет как раз квадрат матрицы. Не квадрат, а...
No, it's not square, it's
just the product of C times C. Here, let me choose some orientation. We now can forget about the loop, then C of G will be let me number somehow edges 1, 2, 3, 4, and this will be 1. It's negative 1, 1, 0, yeah? Where is 1? 1 if V is the target, then V is the target, yeah. Negative 1, 1, 0. 2 is negative 1, 1, 0. 3, 0, 0. Negative 1, 1. 1, negative 1. Here is the incidence matrix. And if we transpose it and multiply, then we must obtain that matrix. Yeah, but it's easy to check.
So yeah, we just should multiply this matrix definition, and we find out that it really works like this. Okay, now I'm going to prove that the Laplacian matrix is positive semi-definite. Well, let me pick some. Let me pick some x. It is a vector whose he lives here. So which is just a vector whose coordinates are labeled by the vertices of our graph. And our matrix can so I can multiply our matrix by this vector and consider the following inner product. And I want this product to be non-negative for any x. Well, I can write QG like this. So I have the following inner product. And this is just the same that as the inner product of C transpose X and itself. And this guy is surely non-negative. This proves yeah.
Sorry, if there are 0 eigenvalues, it should be non-negative.
No, as I write here, semi-definite, so it means
semi-definite.
That's okay.
that zeros are allowed.
Yeah, there is a rather strange style when denoting the space of the vector space spanned by the vertices of a graph. This style consists in writing L2. L2 means functions that can be summed with squares, функции, суммируемые с квадратом. Поскольку это конечное множество, как-то в высшей степени странно обозначать пространство функций на этом множестве через L2. Или это не то? Это не то, это вроде...
Не, ну это то, но I also was a little bit surprised by this notion, but I copied it from the article.
Вершина является ортонормированным базисом.
Да. Множество вершин ортонормированный базис, как мы видим. Нет, CTX лежит уже в другом пространстве, это ну да, но все равно множество вершин ортонормированный базис. Вот. This choice of notation comes from the idea that we will define probably the Laplace operator. And Laplace operator usually is applied to functions that can be summed with squares in L2 or so. Probably this is this reason, but generically I don't know why one should choose such a notation. Okay.
Okay, yes, it makes sense. Well, then we should prove C. Yes, and as we said, if we have several connected components, then our matrix is just a block matrix, and it means that it is sufficient to prove this statement for the case when our matrix is our graph is connected. So we assume that G is connected, and what we want to prove is that that the multiplicity of 0 value is 1, and in other words, that rank of Laplacian matrix is n minus 1. And I'm going to prove it here. Okay, I'll read these examples.
Sorry, maybe
What?
maybe it's a good idea to compute the eigenvalues of this matrix. So that is that easy or not? What are the eigenvalues? So that we can check. Just leave the matrix here and do not erase it. We will see.
But even not computing eigenvalues, we can see that this matrix is likely to have rank 2.
Is it possible to represent it in this form, C times C transpose? How to do this explicitly?
But we have done it. We have computed the matrix C for that one. Yeah, exactly. That's. Yeah, but just continue. Yeah.
Well,
Запусти математику, пусть посчитает.
I was going to tell some another proof of this fact, but in this moment I understand that it can be it is likely to it can be proved easier if we consider this form. We have this equality, and that's why rank of Q is just equals to the rank of C. Okay, and it is sufficient to prove that rank of C is greater or equal than n minus 1. We already know that it's not greater than n minus 1 since we have 0 value, and why it is greater or equal. Maybe if I consider some, so we have, that G is connected, and let us consider some spanning tree of G.
Spanning tree, yeah?
Yes.
Please remind
it is just
everybody
such a tree that it is on the same vertices as the initial graph.
A spanning tree is a subgraph
And,
of a connected graph that contains, which is a tree and contains all the vertices of the graph.
Yes.
And it's
Right.
a tree, yeah.
Okay, then I can consider the matrix C for this tree. Well, it will it consists of it is some submatrix of C, because we just should take columns which correspond to edges that are in the tree, and all columns. So this matrix has n-1 columns, since tree on n vertices has n-1 edges. And it is not difficult to see that all these columns are linearly independent.
That's true.
Yes, maybe one can prove this by induction, deleting some vertex of degree 1 from the tree. So if we
A leaf, yeah. Okay, yeah, it works.
Yeah, so if we remove such a vertex, then what happens with the matrix? We have some row corresponding to this vertex, and since this vertex has degree 1, here all but one elements will be 0, and one element corresponding to this edge will be a 1 or minus 1, or minus 1. And that's why if I remove this column and this row, then the rank of the matrix will be it decreases by 1. And this proves this statement.
Okay, yeah.
Okay.
Так что, Максим, ты не сосчитал, какие собственные числа в этой матрице? Какие?
У меня 5, 3, 0 получилось.
5, 3, 0. So,
У нас получилось, что равно 2,
да.
да? Ну да, 5, 3, 0 вроде.
This is lambda 1, lambda 2, and lambda 3. Lambda 1 is 0, and the other two are positive.
One useful note that it's obvious, but useful that the sum of all lambdas is just the same as the trace of this matrix, so it is the sum of degrees of all vertices in our graph. And that's why it's just twice the number of edges. Okay, then
Here we have sum of lambdas is 8. And it is twice the number of edges. Yeah?
then I'm going to talk about operations on graphs and how they affect the spectrum, the Laplacian spectrum. The first result here is the following. So let's add some edge to the graph. So we have graph G, and let G prime be just G plus some HE. So if we consider the weighted graph, then it means that we increase the multiplicity, the weight of this H by 1, and if it is usual graph, then we just draw one another edge between these two vertices.
And the set of vertices remains the same.
Yes, the set of vertices remains the same. Then the Laplacian eigenvalues of these two graphs interlace. Namely, I mean the following. So we have this chain of inequalities. Note that not all these inequalities can be equalities, since we have the sum of Laplacian eigenvalues of the initial matrix is less than the sum of eigenvalues of the new matrix, because of this. And that's why when we add an edge, the spectrum changes somehow, but we can but this chain of inequalities is true. And this is it is an easier corollary of Weyl inequalities. Let me.
Of which inequalities?
Weyl, maybe.
This name should be pronounced Weyl.
Weyl, sorry. Okay, Weyl inequalities.
Sorry, in the formulation of theorem, sometimes prime is put to lambda, sometimes prime is put to g.
Yeah, thank you. Let me fix it. So.
Они по-разному пишутся. Один через Y, а другой через I. Herman Weyl и Андрей Вейль.
Check which.
Grigorii.
Yes. Okay.
Okay. In this example, Grigorii,
Yes.
in this example, the eigenvalues are integers. Is it always the case, or?
No, it's not always.
Not always the case. It's just some strange coincidence. And
I suppose.
Okay.
No, that they're not always integers. Yes. So what this inequality about? It is so let's consider the following situation. We have some Hermitian matrices, and one matrix is the sum of another two matrices.
Я убрал одну ребро, они перестали быть целыми.
And we consider their eigenvalues.
Вообще рациональными.
Нет, квадратура уравнения.
Ну да.
Then we have the following inequalities. Where for any indices such that the following is true. So we have some bunch of inequalities on the eigenvalues of these three matrices, and they can be described by this formula. And this is the straight corollary. We just should apply this. So we have so I have the Laplacian matrix of the graph G prime, which can be obtained from the Laplacian matrix of the initial graph by adding some matrix of this form. So we have some ones on the diagonal, we have ones here, and all other elements are 0. This matrix, it has rank 1, and its eigenvalues are something. You mean?
Otherwise, we will not
Yes. So
we will not preserve.
Minus ones.
Yeah. Otherwise, we will not preserve the sum
Yes,
in
thank
each
you.
column or row is 0.
Okay, and what I know about this matrix is that it has rank 1, and it is also positively semi-definite. In other words, its eigenvalues are something like this. All but 1 are zeros, and here we have something. And then we use these inequalities for the following indices. We just put g equals 1, g equals y, I, k equals 1, r equals plus 1, and s equals n minus 1. And I just these two summands will be 0 because it will be row 1 and row n minus 1, they all zeros from here. And we just obtain that what we needed. Well, some other situation when we have the decomposition, the factorization of our graph like this. Here I mean, so this is decomposition, and I mean that the graphs J1 and J2 have the same vertices. And the edges of G is the in the disjoint union of the edges of these two subgraphs. And then we have the following statements. Firstly, some statement about the...
do you suppose that both G1 and G2 are connected?
No, it is not supposed.
No, it's not.
No, it's not even supposed that G is connected. It's true. Firstly, some statement about the largest eigenvalue. So the largest eigenvalue of G is not less than both lambda n for the summands, but it is not greater than their sum. And also we can write down inequality for lambda 2 for the second smallest eigenvalue, and it is less or equal than the sum of lambda 2 for summands. So we see here we, sorry. It's here. So here we have this inequality, and here for lambda 2 we have the opposite inequality.
But
no, it's not. It's quite easy fact, and it's even not the graph theory. It's some linear algebra. Since if I want to, since the Laplacian matrix of G is just the sum of Laplacian matrix for summands. Maybe it's even some particular case of these inequalities, or one can prove it directly. But I maybe I won't prove it now, since it is
just
quite easy.
skip the proof.
It is just some linear algebra. Okay, now there are many.
Там лямбда 1 всегда 0, да?
Лямбда 1 всегда 0, да.
А если вот я говорю о второй точке, если на первой лямбда к 0, то для лямбда к вторая точка тоже будет, да?
Yeah. Suppose all lambda 1, lambda 2 up to lambda k are 0. Then our graph has k connected components, yeah? K connected components, and the question, I believe that yes, that we can, then each of the graphs, G1 and G2, has at least k connected components, and we can proceed for each connected component independently. And this will be the lambda 2 for each connected component.
Вообще про это можно думать? Вот это и просто сделать как какую-то версию формулы включения и исключения, но может быть с неравенством.
Нет, это не включение исключение. Это не включение исключение, это другое.
Well, now I'm going to finish with the operations on graphs. In the article, there are considered some other operations, also like they are also considered Cartesian product of graphs. Or I can consider join of two graphs. It is just when we take this joint union and then add all of two graphs and then add all vertices between the two halves. And also there are some other operations, and for each operation there is some nice formula for eigenvalues, and that's why one can say that these eigenvalues are quite natural, since they behave nicely under natural operations. So now I move to the next part of the talk, and it is devoted to Matrix-Tree-Theorem. So this is the most interesting thing, since now we are going to establish some relations between some graph invariant and and our lambdas. And what we are going to consider here is just the number of spanning trees. I will denote it by kappa of G. And the theorem is the following.
Is it the number of spanning trees or spanning forests or
It is the number of spanning trees.
spanning trees? So you assume that the graph is connected.
Yes. No, well, maybe it's not
Otherwise, the
connected then.
number of spanning trees is
No, maybe I suppose we can not assume that, and if G is not connected, then the number of spanning trees will be just equal to 0. Okay, then the theorem is the following. So I'm going to this number is equal to any n minus 1 by n minus 1 minor of the Laplacian matrix up to sign.
So we take the Laplacian matrix, we delete one column and one row in an arbitrary way, and then we obtain an n minus 1 times the n minus 1 matrix whose determinant is exactly the number of spanning trees.
Plus or minus? No,
Up to sign. Yeah.
Okay, let us prove this fact. Firstly, let me note that it is easy to see that all such minors are equal to each other up to sign. It's easy to obtain from that fact that all the elements in any row sum up to 0, and in any column also sum up to 0. So I can obtain any minor from any other minor by removing or adding rows or columns, and under this transformation the determinant cannot change. The determinant can only change its sign. And that's why I'm going to pick some particular minor and deal with it. So which minor I'm going to pick? It will be the diagonal minor. So I'm going to throw out some row and ith row and ith column for some I. And but I is not arbitrary. I'm going to pick such a vertex. Okay, yes, let's suppose that indeed G is connected.
Otherwise, we are done.
Yes, otherwise both parts are just 0.
Both parts are 0, yeah.
Then there exists such a vertex that if we remove it from the graph, then it remains connected. Well, for instance, one can pick some spanning tree of the graph and remove any of its vertices which have degree 1. So I'm going to pick such a vertex. Suppose that my vertices are labeled by numbers from 1 to n, and this is the first vertex.
Вообще такое замечательное рассуждение, что из связанного графа можно удалить какую-то вершину, что он останется связанным. Берем остовное дерево и выкидываем его лист. Тогда оно останется остовным деревом урезанное остовное дерево останется остовным деревом в меньшем графе.
Okay, so I'm going to consider, so this is the first, I throw out the first row of the first column, and I'm going to consider this minor. Okay, and here I also will need our old friends, which are matrices of incidence for oriented graphs. So I pick any orientation of G, consider the corresponding matrix C, and we also remember that we have this inequality. So let me draw it here. This is C transpose, and here we have the Laplacian matrix of our graph. Okay, then I am going to throw out first row and first column from here, and that's why I'm also going to throw out first row from here and first column from the transposed matrix. Then I'm going to, I need the determinant of this minor, let it be M11. So I'm going to compute the determinant of M11, and it is just the following thing, which is called Cauchy-Binet formula, and so it is equal to the following. Sum of such products where A is some subset of the set of edges.
An arbitrary subset, yeah?
No, not arbitrary, but of the proper size. So the size will be
which is the proper set.
n-1.
Mm-hmm.
So here I, in this formula, I write CA and CA transpose, assuming that I have already thrown out the first row and the first column.
Mm-hmm.
So we just consider all ways to pick here n-1 column, then we compute the corresponding determinant, take the corresponding determinant here, multiply them, and sum up over all choices of n-1 column. And this will be the determinant of this manner. So it is also some classical linear algebraic result, and I'm going to use it.
Mm-hmm.
And now so what is the choice of this subset A? So I just take my graph and choose, this graph has n vertices, and I choose n-1 edge. So some set A of edges. Then I can consider the graph on the same n vertices which has these A edges. And note that this graph is a spanning tree if and only if it is connected.
Will you repeat, please?
I pick n-1 edges of my graph and consider the graph which has the same vertices and these n-1 edges. And I consider two properties. The property to be a spanning tree of the initial graph, just to be a tree, and the property to be connected. And I claim that since we pick n-1 edges, then these two properties are just the same.
Mm-hmm.
So if we have a graph with n in other words, if we have a graph with n vertices and n minus 1 edges, then it is a tree if and only if it is connected.
Mm-hmm. Yeah, it's clear.
Okay, now let us
So we have one if and only if A is a spanning tree. This product of determinants is one if and only if A is a spanning tree. Otherwise it is zero, yeah?
yes. If so, it is one if graph A is connected. So yes, I denote here the A, it is just the graph which has the same vertices and edges from A. So if it is connected, and 0 if A is not connected. If it is true, then we are done, because we know that to be connected is the same to be a spanning tree, and that's why we have just some zeros and some ones in this sum, and the number of ones is just the number of spanning trees, and so we are done. And why it is so? It's we know the
But we have proved this already. I believe the proof is finished, no?
No, I haven't proved that the determinant of this guy will be 1 if A is connected.
But
It will be plus or minus 1 and then b squared by multiplying by the determinant of
plus or minus 1, indeed.
Yes, it is plus or minus 1. Yes, and why it is
But
plus
when we
1?
multiply by the determinant of the transpose matrix, then it will be 1 anyway. The product of two negative ones is 1. Вы же сказали, как это доказывать удалением листов. По индукции удалением листов.
Yes, indeed. So this, yes, indeed. We can consider the same procedure with deleting of leaves, and then by induction we indeed obtain that the determinant is 1 or minus 1. Yes.
Yeah.
And so we are completely, the proof is completely finished. Okay, we have not very much time left, and that's why I'm going to stand a couple of results without proof, but this is also rather interesting and important.
Aren't you planning to continue next time?
Maybe yes, it will be nice, because
Yeah.
there are some interesting
Okay,
results left.
then you'll continue next time, and don't hurry. So you
Okay.
have just a few minutes. You may say.
Okay, so the next part of the talk is devoted to the second, smallest eigenvalue of the Laplacian, and it turns out that it is very important, and many different graph invariants can be are connected somehow with lambda 2, and we are going to consider. For example, we are going to consider such invariants as vertex connectivity and edge connectivity. So it is, I'm not giving the formal definition, but intuitively it is about how many, if we are talking about the vertex connectivity, it is about how many vertices can be removed from the graph without losing its connectivity. And the same about edge connectivity. So it turns out that there are some interesting results
So H connectivity over tree is 1. Yeah.
H connectivity is
Over tree.
over tree. It is 1.
Yeah.
So if
because
we have
deleting an edge, we always we can delete an edge and increase the number of connected components. Or even a graph has a bridge, then its connectivity is 1. It's connected and have its edge connectivity is 1. Okay, yeah, and
Okay, and there is such a result that these two guys can be estimated from below by lambda 2. Well, indeed, the vertex connectivity is less or equal than the edge connectivity, and we have such chain of inequalities. This is also some classical fact from graph theory. It's not about the Laplacians, but this estimate is quite interesting, and we are going to prove it next time.
Okay, let me add a few words. Thanks, Grigorii. We'll continue next time.
Yes, thank you very much.
Let me add a few words. Laplacians and eigenvalues of Laplacian eigenvalues of graphs is a well-established subject. It started for long decades, and there are many probably remarkable results obtained in this way. This is the first time we discuss this subject in our seminar. This is because I do not know any connection of Laplacians to Vasiliev invariants, of knots. But probably they exist, but I never managed to find any. Nevertheless, this year I decided that we discuss this Laplacians because they definitely are related to cluster algebra structures. And these Laplacians, for example, when we add weights to the edges and consider these weights as what's called проводимость по-английски. Conductivity. I don't remember. Conductivity of edges, and then we obtain an electrical network, which is one of the main objects of study in cluster algebra theory, and the corresponding Laplacian also plays a rather important role in these constructions. Probably we will have some experience and some problems are related to this construction in the nearest future. Thanks once again. And we have a break. Спасибо, Grigorii.